Hey everybody, welcome to today's video, which is the third part of our discussion of wave behavior. And I'm calling this one So What? Because we're finally going to talk about how wave behavior applies to chemistry. So in an earlier video, we looked at wave behavior and said that forms of radiant energy each have their own unique wavelength and corresponding frequency. Those two properties are inversely related to each other such that their product is equal to a constant. That constant is the speed of light. Okay, and then next we talked about Max Planck and Albert Einstein's work, in which they theorized that even though radiant energy travels as a wave, it also has some properties of particles, and they called those little chunks of energy photons. Now remember, we're not saying that light exists as particles. It does not. It's an energy form, but the energy can be quantized or chunked. And then we said that you can actually calculate the energy of a single photon using this equation. So the energy value for any given form of radiant energy is simply Planck's constant times the frequency. All right, so let's see how this is going to help us in chemistry. You remember the photoelectric effect that Einstein got his Nobel Prize for discovering. So this is where we recognize that radiant energy can strike a piece of metal and can possibly dislodge electrons from those metal atoms to generate a stream of electrons, which is electricity. So we're saying that photons of this radiant energy may have enough energy to do one of several things. We saw when we did flame test lab that those photons might actually excite electrons to a higher energy level. In this photoelectric effect, the photons may have enough energy to knock an electron off an atom entirely, or in our next unit, we'll talk about the possibility that they might be able to break a bond in a molecule. Okay, let's go back to this photoelectric effect. We have to choose a metal to put in the device. So I'm going to have us consider, first of all, the metal beryllium. Okay, and beryllium has 4 protons in its nucleus and 4 electrons outside the nucleus. Those 4 electrons are in the 1s sublevel, and then there are 2 electrons in the 2s sublevel. And these 2 electrons in the farthest energy level from the nucleus are the valence electrons. Now, you remember that in an earlier unit, we also said there's a Coulombic attraction between positive and negative particles. And energy must go in to pull them apart, to overcome that Coulombic force of attraction. So I'm talking here about the positive protons and the valence electrons. The Coulombic attraction draws them to each other. But if you wanted to knock off one of these electrons, totally remove it from the atom, then energy has to go in. And we refer to that energy as ionization energy. For beryllium, that ionization energy is equal to 900 kilojoules per mole. Now let's consider another alkaline earth metal, calcium. Calcium has 20 protons in the nucleus and 20 electrons outside. And those 20 electrons are found in the 1s. The energy level 2 has an s sublevel and a p. Energy level 3, the s sublevel and the p sublevel are filled up. And then the 4th energy level has 2 electrons in the s. Again, 4th energy level for calcium is the farthest from the nucleus, and these 2 electrons are the valence electrons. So I'm asking now, what do you think the ionization energy to remove one of these valence electrons from a calcium atom, how do you think that would compare to that of beryllium? Would it also be 900 kilojoules per mole? Or do you think it would be less? Or do you think it would be more? So as you ponder that for a minute, I also want you to remember what we've said earlier about Coulomb's law. Coulomb's law tells us that the force of attraction between, in this case, positive protons and negative electrons, that force of attraction gets weaker when distance gets longer. So as we're looking at calcium, the distance between the positive protons and these valence electrons that we want to remove, that distance is much longer compared to the distance we had to consider for beryllium, which means the force of attraction between these protons and these electrons is weaker. And if the force of attraction is weaker, the ionization energy should not be as high. And in fact, the ionization energy is 369 kilojoules per mole. So, back to our photoelectric device. If our metal inside this device was beryllium, the radiant energy would have to be at least this strong to remove valence electrons. If our metal inside was calcium, then the radiant energy would have to be at least this high to remove the valence electrons. All right, so let's consider some radiant energy whose frequency is 1.43 times 10 to the 15 per second. How much energy do those photons have? So this is our energy equation for a photon. We take Planck's constant and we multiply it by the frequency of the radiant energy we're considering. And when I multiply these two together, and my second cancels out my per second, this gives me the very, very tiny energy of single photons of this particular radiant energy I'm using. Remember, guys, this E value, when you use this equation, is always going to be very small because this is the energy of each photon. So really, this answer is the joules of a photon. Okay, now I want to go back to my picture for just a minute. This radiant energy that's coming in and striking the piece of metal is made of a fleet of photons, many, many photons streaming along. Okay, one photon either can or cannot do the job of knocking off an electron. But if it has enough energy, then one photon would strike one beryllium atom and knock off one valence electron. Okay, that photon has done its job. But here comes another photon, striking another beryllium atom and removing the electron from the second beryllium atom, and so on. So I want you to really be clear that these photons, if they have sufficient energy to do the job, then each one has the opportunity to hit one atom and remove one of its valence electrons. And then the second photon would come along to the second electron. Now, when we were considering beryllium, our ionization energy was given in kilojoules per mole. So this is talking about how much energy would be needed to remove electrons from a mole of beryllium atoms. Let's go back to our photons and see what the energy of not one photon would be, but let's suppose we had a fleet of photons, a stream of them. Let's suppose we actually had a mole of photons attacking a mole of beryllium atoms. So here is my energy of each photon, and now I'm going to use Avogadro's number and say that there's Avogadro number of photons in a mole of photons. And my unit, photon, divides out. And the last thing I want to do is use this equivalence, which reminds me that there's 1,000 joules in a kilojoule. I have the unit joule in the numerator, so I'm going to say 1,000 joules is equivalent to a kilojoule. Joules, divide out. Do you see now how my unit is kilojoules per mole? And when I multiply, I have, can you see all that? So here was the energy of my photon, 9.48 times 10 to the negative 19. I am multiplying that by Avogadro's number. That's my numerator. And I divide by, and I always put my denominator in parentheses. My denominator is 1,000. So this 571 kilojoules per mole is the energy of a mole of my photons. Beryllium has an ionization energy of 900 kilojoules per mole. My mole of photons does not possess enough energy to knock out the electrons in beryllium. This stream of photons would hit a mole of beryllium atoms and just basically bounce off. The energy of these photons cannot do this job. But if the metal inside my device was calcium, whose ionization energy is 369 kilojoules per mole, a mole of my photons is sufficient to remove a mole of electrons from a mole of calcium atoms. So the radiant energy that I'm considering here, the mole of photons has enough energy to ionize a mole of calcium. Okay, guys, that was a lot of math. We'll have lots of practice with that. And then when you're comfortable with calculating the energy of your photons and considering if that energy matches ionization energy needed, then we'll move on and look at the energy of your photons and see if it is sufficient to break a bond in a molecule. All right, guys, thank you.